Now we will look at the topic of buoyant force and the Archimedes principle. Okay. Before, when we talk about the Pascal principle, we look at a fluid. Okay, and we separate the fluid into two parts. This middle part, and we assume that, or we take it as an object. Okay, and the surrounding fluid exert the force to the object. Okay, and at this time we know that the force exerted by the fluid. Okay, if I write down it as the force of the fluid. The force of the fluid is equal to the rho GV, and this V is the volume of this part. Okay, and rho here is the rho of the fluid. Okay, and G is the gravitational acceleration, which I may write this as m of fluid G. Okay, since these two terms, is the m. Okay, so we can say that the force that exerted by the fluid is equal to the weight of the fluid in the volume V. Okay, this volume V is this. Okay, so it means that the force from the fluid surrounding this volume V, the force of the fluid surrounding this volume V is equal to the mass of the fluid inside this volume. The question is that if we replace this volume by the real object, okay, now if we put the real object here, you can see that the fluid surrounding the object is the same. Okay, only the object change from the fluid itself to the real fluid. So the fluid surrounding this object is the same, right? And the force exerted by the fluid surrounding this volume is the same too. So it means that if you put an object in the fluid, it will experience the force from the fluid, and this force, the magnitude of this force, is equal to the weight of the fluid that is replaced by the object. Okay, because before the fluid is in this volume, right? But when you put the object in, the object replaces the fluid here, right? So it means that if this is a fluid itself, we know that the force exerted by the surrounding fluid is equal to the weight of the fluid here. When you replace it by the object, the surrounding is the same. So the force exerted by the surrounding fluid is equal to the weight of the fluid that is replaced by the object. Okay, and that force is called the buoyant force. And this principle we call it the Archimedes principle. We will talk about it soon. We can also understand the buoyant force this way also. That is, if you put an object in a fluid, this object, okay, and you can see that at the top of the object, the top surface of the object, it will experience the force from the fluid. Okay, if the area here is A, so the force at the top, let me say that the force at the top is equal to the pressure at the top times area. Okay, and the pressure at the top is equal to the P0 plus rho GH top. Okay, where HT is a distance from the surface of the fluid to the top surface of the object. So this is a HT. Okay, this is the HT, and also it will experience the force at the bottom surface. Okay, so we put this as F top. Okay, and also it will experience the force from the pressure at the bottom surface. We call it the F bottom. And we can write out the expression for the F bottom like this. F bottom is equal to the pressure at the bottom times area A, which is equal to the P0 plus rho GH bottom, use small b. Okay, and small b here too. Okay, so the net force in the vertical direction, okay, this is HB. Okay, this is HB. So the total vertical force F is equal to FB minus FA, okay, which is equal to the rho GHB minus FA, okay, which is equal to the rho GH, sorry, we missed one term. We should have A here, okay, so A here and A here, so we have this rho GHA. This HA is the volume of the object, okay, so we have this as a rho GV, okay. This rho again is the density of the fluid, so if we want to so we can write it as a M of the fluid G, okay, where M comes from the product of rho and V, okay. So we have the force, the net vertical force is equal to the weight, this term. This term is the weight of the fluid inside the volume V, okay. So we have the same conclusion that the net force exerted by the fluid to the object is equal to the weight of the fluid that is replaced by the object. Someone may have a question that don't we have the force in the horizontal direction? The horizontal direction. Yes, we have the force on the horizontal direction, but you can see that from the symmetry, the force on the horizontal direction will cancel. For example, in this figure, the force exerted to the right, okay, the force exerted to the right, this force will cancel the force exerted to the left. So we don't have to calculate the force in the horizontal direction. But in the vertical direction, it's not symmetry because the height HT is not equal to the height HB. So it's not symmetry. So we have the net force in the vertical direction and equal to the weight of the fluid inside the weight of the fluid that is replaced by the object.